Hello and welcome to Summer 1 Week 4 Year 10 marking exam. This one is on the Resistors practical. Remember to have your green pen ready for marking, blue pen ready for making annotations. Okay, let's get started. First one says, complete the sentence, choose the answer from the box. We've got charge, energy, potential difference and resistance. Electric current is the rate of flow of charge. One mark there. Figure 1 shows a parallel circuit. And it's asking us to calculate the current measured by the ammeter A2. It's this one here. We can see that we've got two different branches in our parallel circuit. One here and one here. Before the branches, the current is 0.56 amps. Okay, and we're thinking about current in a parallel circuit. Remember, always draw your little table for series and parallel. Remember, in series, current stays the same. And as long as you can remember that, you can remember all the different rules. So it therefore splits in a parallel circuit, potential difference splits in a series circuit and stays the same in a parallel circuit. So what we're looking at today is we're looking at current in a parallel circuit. So we're thinking the current is going to split. Here we've got 0.56, 0.43 amps are in this branch. So therefore I'm thinking the rest of the current must be coming down here going through A2, so we do 0.56 minus 0.43 and we find the answer to be 0.13 amps. One mark for that. Okay, next question is a calculation question. 1C, the circuit is connected for 300 seconds. I've bugged my question, underlined it, put a T for time. The total current in the circuit stays at 0.56 amps. I for current, calculate charge, capital Q. So they're given the equation here. We're going to list our values, state the equation, substitute in our values, 168 coulombs. Next question follows on from this. Potential difference supplied by the battery is 4.5 volts. Calculate the total energy transferred in 300 seconds. We're going to use the charge that we calculated in the previous question, which was 168 coulombs. So again, I'm going to list my values, state the equation which they're very kindly given to us, substitute in my values, 756 joules. 2 marks available there. Okay, figure 2 shows a series circuit. Resistor R2 breaks, so that's why I've crossed this out. What happens to the reading on the ammeter? To understand this question, we need to understand for current to flow in a circuit, we need a power supply, which we've got here. Fantastic. We need everything to be made of electrical conductors, which we're assuming they are, and we need a closed circuit with no breaks in it. Well, here in our series circuit we would have a break, a gap in the circuit, so we don't have a closed circuit, therefore current cannot flow. So we would say that the reading on this ammeter decreased to 0, or you could say the reading would be 0 amps. 1 mark there. Okay, 1F. Figure 3 shows a parallel circuit. In this one, R3 breaks. What happens to the readings on the ammeter? They're going to be asking about A2 and A1. Okay. Now with A1, we can think it's very similar to our series circuit. If I cover up this part here, and we've just got one loop going around here, if this breaks, I've got a gap, and therefore current cannot flow down this branch. So on A1, we're not going to have any current flowing through that ammeter. So we could say that the reading would decrease to 0 again, be 0 amps. For A2, it's a little more complicated what would happen. Here we're losing a resistor. Let's first of all talk what happens if we add resistors in parallel. So if I was going to have one branch and I was going to put on another branch with a resistor on it. If we add a resistor in parallel, the overall resistance of the circuit actually decreases. This is because we've got more options, more branches for the current to flow down. A bit like if we opened another ticket barrier at Wembley Park, there'd be more barriers for people to flow through, the flow of people would happen quicker. So the resistance goes down, so the current goes up. Remember, we call this relationship inversely proportional. Therefore, if we remove resistors in parallel, we're going to see the opposite happen. The resistance is going to go up. Therefore, the overall current in the circuit will decrease. So, what is going to happen to A2? The ammeter reading will decrease. It won't decrease to 0. If you wrote that, you wouldn't get your mark here. It would just go down. Figure 4 shows the circuit symbol for 3 different components. Okay, and I've just labelled them here. This is a variable resistor. This is an LDR, or a light dependent resistor. And here we've got our thermistor. We should know our circuit symbols. Which component is a variable resistor? We've already done that. That is A. Which component is a thermistor? Already done that. C. Which component will resistance decrease when the temperature increases? Think about temperature. Therefore, it's going to be affected. We're going to be thinking about a thermistor. So that is C. And in which component will resistance decrease when light intensity increases? Think about light. That's going to be our light dependent resistor. B. 1 mark for each of those. Okay, next question. Figure 5 shows 4 different arrangements of resistors. Here they are. Now, before I go any further, I'm just going to calculate a total resistance in each of these. These resistors are in series with each other. That means to calculate a total resistance, we simply add the two together. So this would be 10 plus 10, which is 20 ohms. Very simple here as well. 5 plus 5, 10 ohms. With our parallel circuits, we don't find an exact value. For our parallel circuits, we say the total resistance is less than, and then we say the value of the smallest resistor. Now here they're both the same, so we say less than 10 ohms. And here we would say the total resistance would be less than 5 ohms. Okay, let's have a look at our question. 2 of the arrangements are in series, and 2 of the arrangements are in parallel. Describe the difference between a series and a parallel arrangement. Okay, 2 marks on offer here. One way you can get your 2 marks is by saying in a series circuit there's only one path for current, whereas in a parallel circuit there is more than one path for current. 1 mark, 2 marks there. Or to get your marks, you could talk about the potential difference and say in a series circuit potential difference is split between the components, whereas in a parallel circuit it's the same across all of the components. So 2 ways you get your 2 marks there. Which arrangement has a resistance of 10 ohms? I've already worked that out up here. Well done me. That is R. Which arrangement has the highest resistance? Again, just looking at my 4 numbers I've worked out here. 20 is the highest number, so that is P. A student connects a resistor to a cell for 60 seconds. The current through the resistor is 0.97 amps. Calculate a charge flow, and pay attention to this. It's asking us to give our answer to 2 significant figures. I've bugged my question. T for time, I for current. Calculating charge, 2 significant figures. Listed my values here. Write my equation, Q equals I times T. Substitute in my values. I find my answer to be 58.2, but remember I need to round to my 2 significant figures. So my answer is 58 coulombs, 2 significant figures. 3 marks for that. If you forgot this significant figure part, you can have 2 of your marks. Okay. Figure 6 shows 3 circuits. The resistors in the circuits are identical. Each of the cells has a potential difference of 1.5 volts. Okay, so here's our circuits. I've just started off by working out, therefore, the total potential difference of the power supply. So 1.5 volts, then you've got 2 cells, so 1.5 plus 1.5 is 3. 3 cells, 1.5 plus 1.5 plus 1.5, 4.5. I've also worked out the values on these voltmeters as well. So as this is the only component in the circuit other than the cell, all the potential difference of the cell is going to be across this resistor, so this one will be 1.5. Similarly, only one resistor in this circuit, so all the potential difference will be across this resistor, so that will be 3 volts. Here a little bit more complicated. We need to look at the question. It says the resistors in the circuits are identical, So if these two have identical resistance, then the potential difference will be shared equally between them. So 4.5 volts shared equally between the two of them is 2.25 volts. So this one will be 2.25 volts. Okay, use the correct answer to complete the sentence. The resistance of circuit 1 is half the resistance of circuit 3. Calculate the reading on voltmeter V2. Well, I've already done that here. That is 3 volts. Which voltmeter will give the lowest reading? Again, I can already work that out from my annotations. That is V1. Okay, last question. A student wanted to find out how the number of resistors affects the current in a series circuit. So think about this is some sort of investigation. So we're going to be changing the number of resistors. So that would be my independent variable. And how it affects the current, that's what I'm going to be measuring. That would be my dependent variable. Figure 7 shows the circuit used by the student. So I've got simple battery, switch, resistor, and an ammeter. The student started with one resistor and then added more resistors to the circuit. And these are again identical resistors being added. Each time a resistor was added, the student closed the switch and took the ammeter reading. And the student used a total of 4 resistors. So we've got this circuit, they're going to have a resistor in there, close the switch, take the reading, open the switch up again, pop another resistor in, close the switch, measure the current, turn it off, put another resistor in, and so on. Figure 8 shows 3 of the results obtained by the student. Okay, so they put them in a bar chart here. Immediately we can see current in amps on our y-axis and the number of resistors in the series 1, 2, 3, 4 on the x-axis. To get valid results, the student kept one variable the same. Remember we talked about our independent and dependent variables. Well, here they're going to be asking us about our control variables. You need to think of a control variable here. Which variable did the student keep the same? That was the potential difference of the power supply. You could have also said the number of cells as well. That would be fine. The bar chart in figure 3 is not complete. The result using 4 resistors is not shown. Complete the bar chart to show the current in the circuit when 4 resistors are used. Okay, so we need to work out what the size of this bar is going to be. We know it's probably going to be less than 1 because we can see as the number of resistors is increasing, the current is decreasing. But the exact value can be a little bit trickier to work out. To do this, what I did was I thought about what is the potential difference of the power supply. I know that V equals I times R in my circuit. I'm going to try and work out the potential difference of the power supply. If I have a look at this first bar, it's telling me that the current is 4 amps when there is 1 resistor in the circuit. Now I'm going to make this easy for myself and say each of these resistors is a 1 ohm resistor, just to make the numbers nice and simple for myself. Okay, so we've got 4 amps multiplied by 1 ohm, so we're going to say the power supply is 4 volts. And we've said that's a control variable, so we're going to keep that the same throughout. Now it might not be, but we're just going to use these numbers to help us out. So let's just see how this works. Let's look at current for 2 resistors. We should be finding the current to be 2 amps. Let's see if we're right. So again, V equals I times R. We've got potential difference of 4. Our resistance is 2 ohms. We're going to say 2 resistors, 2 ohms. Let's see if this works out. Oh, great, it does. 2 amps. Okay, so it seems like my graph is matching my numbers here. Good. So let's see, we need to work out the current when it's 4 resistors. Now I want to put, oops, pardon me, 4 resistors. So V equals I times R. 4 volts again, this time 4 resistors. To find I, I'm going to do 4 divided by 4. 1 amp is the current when there are 4 resistors in the circuit. So, with my ruler, I'm going to pop on a bar at 1 amp. It doesn't matter too much how thick the bars are. Of course, if you want to be nice and neat, you'd make it the same width as the other bars. However, you don't get any marks for that. 2 marks for getting that correct. If you just have a bar less than 1, you can still get 1 mark. If you've got a bar exactly on 1, you get 2 marks for that question. Okay, last question. What conclusion should the student make from the bar chart? Whenever they ask you to make a conclusion from a bar chart, from a graph, you're always going to write a sentence a bit like this. As something, whatever it is, increases or decreases, then your other variable will increase or decrease. That's a sentence I'm going to use whenever I want to write a conclusion from some sort of graph, from some sort of data. So here, as the number of resistors increases, the current decreases for 1 mark. Once you've marked all of that, make sure you go back to the front page and write on your mark out of 27.